the extra thing which appears in the decay of the heat kernel, and anchor G's estimate is actually valid both ways. So it looked like then that in Hardy's theorem you actually have to put a decay of this kind if you want to characterize the heat kernel. So you have to put more decay to pin things down to a single function. Otherwise what is going to happen is a hell lot of functions are going to appear. So the correct decay was this, and then Narayanan and myself, SU was very happy about this statement. So was Professor Sitaram, that if f decays faster than heat kernel and the Fourier transform decays faster than the Fourier transform of the heat kernel, then the function is actually a scalar multiple of the heat kernel. That is what is the version analogous to a v equals to 1/4. Well, now it sounds so trivial, but back then it was not trivial. Okay. In this context, analogs of Berling's theorem was proved by Rudra Sarkar, J.S. Sengupta, and Thangavelu. We shall just present one such version. I don't remember whether somebody has characterized heat kernel in this Berling's version. Maybe they have, I don't remember. So the rank-was version goes like this, that integral over x and integral over a star. You have the function, then you have the Hilbert-Schmidt norm of the Fourier transform. Again, we are working for right k-invariant functions, so class 1 principal series is good enough. Then you have e power mod x, mod lambda. Then you have to throw in a phi naught, a polynomial here. Then this is Harishchandra's C function serving as the Plancherel measure. If d is lesser equals to dimension x, then f turns out to be equals to 0. So this is an analog of Berling's theorem in the context of symmetric spaces. So this is more or less the story up to 2007, but I heard that recently Sanjay Pushti and Sanjay Parui have come up with a version of this for Heckman-Obdam operators. I don't know what it is. Okay, and then some other interesting developments happened around 2006, which is little new. However, SCB knew about it. I remember lecturing this about this to him, that Carlos Koenig and Sagun Chanilo, they independently observed that Hardy's theorem can actually be restated in terms of the free Schrodinger equation. So you have the typical Schrodinger equation here, and suppose the initial data decays like Gaussian, and at certain time t naught, ux t naught has a Gaussian decay. If 16 ab t naught square is bigger than 1, then u is actually 0 for all t. It's as I said, it's really a restatement, because the proof follows by simply applying Hardy's theorem to the fundamental solution, which can be easily written down in the Euclidean context, that Schrodinger kernel is given by this. If you just expand this convolution and write it properly, you will get the Fourier transform appearing here, and where h is this. So by the initial condition, h already has got a decay, because f has got a decay. This is an imaginary factor, doesn't matter much. H hat has got a decay because ux t naught will have a decay. So h hat at x by 2 t naught will have a decay. Apply the standard Hardy's theorem, h will vanish, so will u. An analogous statement for complex semisimple Lie group was proved by Sagun Chanilo in 2006 under the assumption that f is k bi-invariant. A more refined version was proved later by Sundari and Angela Pascual in 2011. It appeared, or it was submitted in archive, I don't remember, around 2011, for Riemannian symmetric spaces of non-compact type with the without the assumption of k bi-invariance. Their technique was to simply apply Redon transform and to push the problem down to the Euclidean context. For Rn, Carlos Koenig and his collaborators have worked further on uncertainty principles related to Schrodinger equation with potential this time. This is an extra factor which is appearing, it was not there earlier. And under suitable conditions on V, they proved that the only solution, u belonging to this space, satisfying this kind of decay, average decay, its kind of Cowling price, is 0 if a square b square t is bigger than half. So it's just a glimpse of the activity centered around Hardy's theorem, which I have seen as a student. So if you want to know more, you can look at this book. I have seen the beginning of writing this book in ISI Bangalore when Professor Thangavelu was giving a course on Hardy's theorem itself. It appeared in Berghauser. And then a recent paper by these 4 people that appeared in Bulletin American Mathematical Society in 2012, Uniqueness Properties of Solutions to the Schrodinger Equations. Thank you.
questions. So if somebody wants to ask Salvatore some
Or the
questions.
previous speaker. Or the previous speaker.
Or the previous speaker, because we have some time for questions.
Let me make a comment. Maybe maybe it's even a wild statement. See, many of these uncertainty principles, which are formulated in this way, if you look at the operator theoretic background, you have a pair of operators, namely the position and momentum, whose commutator is the identity operator, right? So instead of that, suppose you had a pair of self-adjoint operators, A and B, whose commutator, of course, the multiple with identity, the complex number I, is a positive operator which is invertible. What is the kind of framework will you get in that background? What will be the solutions of? I mean, if you take functions in the spectral representation of A and also spectral representation of B, what is the kind of uncertainty principle you'll get in function theoretic setup? So it's a wild question.
Yeah,
So
I don't know. Whether
I know, but
yeah,
it's something that
which
you can
which
think
one
about.
certainly look at. Yeah, yeah. I haven't seen any such.
Because the
thing.
reason I asked you is that in some of the formulations that you see, the inner product x dot y that appears,
Yeah.
the operator corresponding to that, if you take x as a multiplication by x and y as the differential operator, this operator is associated with dilations.
Yeah, yeah.
Okay? And the dilations have an intimate relation with the Laplacian in the sense that the commutator of the Laplacian reproduces the Laplacian itself. So that is why it seems to be appearing, that's what I feel.
Yeah, no, I haven't seen any
So-
such thing before.
So probably a more general framework exists.
Maybe, yeah,
It'll be interesting to see that.
yeah, maybe.
Any other questions about what the previous speaker had to say?
Decays as a Gaussian, then f is itself is 0.
Yeah.
Is it a necessary condition like that both f and its Fourier transform should decay as a Gaussian?
Not.
Okay.
I mean, there are other uncertainty principles which are generalizations of Hardy's theorem, which I haven't talked about. One of them is something called Morgan's theorem, where you have a decay like e power minus mod x power alpha. Fourier transform decays like e power minus mod x power beta. Then depending on certain conditions on alpha, beta, a, b, you can get f to be equal to 0. It is not particularly about Gaussian. However, what can be particular about Gaussian is a characterization from this decay. I haven't seen any analog of characterization except the Gaussian case. But for uncertainty principle, the answer is no. There are other pairs for which you can have.
One more, not the relevant one to this talk. Based on the characterization of the function,
Yeah.
can we talk? Okay, based on the characterization of the function, its decay, how the function is decaying, and its Fourier transform. Can we talk about the zeros of the Fourier transform? Maybe the real zeros. Is it possible to get some idea about the zeros of the Fourier transform?
Pointwise kind of behavior, I don't know much. No. I haven't seen any such result.
Thank you.
Any other questions?
So what is the relationship between these types of these formulations and say the Heisenberg formulation?
Heisenberg formulation is another uncertainty principle. It's not necessary that they should be related. There are a hell lot of uncertainty principles. It's just one of them.
Any other comments or questions? I'd like to make one comment. The connection with heat kernel was actually pointed out by V.S. Varadarajan, and he was the one who suggested that one should look at, for the analog of the Gaussian, one should look at the fundamental solution of the heat equation, you know, so in the general case, in the general Riemannian case. So, or rather, he, when he was the editor of Pacific Journal, one of the referees for one of the papers pointed out that that the case of AB equal to 1 or 1/4 or whatever is connected with the behavior of the fundamental solution of the heat equation. Thank you. So, sorry?
We'll reconvene at 4:30.
So we will have coffee and reconvene at 4:30 for the second part of this afternoon session, which will be chaired by